race between two cylinders is performed. Both cylinders begin at the top of the 1.5 meter tall ramp and roll without slipping to the bottom. A, what is the speed of the hollow cylinder when it reaches the flat? B, what is the speed of the solid cylinder when it reaches the flat? And C, which one would win the race? This problem is an energy problem. The reason we recognize that readily is that we are given a 1.5 meter height and we are asked for a velocity at a later point in time. Height will relate to potential energy, velocity will relate to kinetic energy, and using energy methods will yield us solutions very rapidly. Let's begin with the hollow cylinder. The style by which we solve an energy problem is to identify two moments and then connect these moments with energy principles. In this problem, the two moments are clearly the moment just before the hollow cylinder is released and the moment after the hollow cylinder is rolling across the flat surface. We will connect moment 1 to moment 2 using the principles of energy. The first question we ask ourselves in any energy problem is whether there is any work due to a non-conservative force between moment 1 and moment 2. In this problem, the work due to non-conservative forces between the two moments is equal to 0, and therefore we will apply the principle of conservation of energy. We apply this principle by setting the total energy at moment 1 equal to the total energy at moment 2. And since we now understand that there are two forms of kinetic energy, translational and rotational, we have to ask ourselves 4 questions at each of the two moments to fill out our energy equation. Let's begin with moment 1. At moment 1, do we have translational kinetic energy? The answer is no, because we have no velocity at moment 1. At moment 1, do we have rotational kinetic energy? The answer is also no, because at moment 1, the object is not yet rotating. At moment 1, do we have gravitational potential energy? That depends. In each problem, we'll need to set a location for height or y equals 0. Most often, we choose the location at which the object is lowest to be the y equals 0 location. We'll choose that, therefore, at moment 2, and so at moment 1, we do have a gravitational potential energy equal to the mass of the object times g times the height or y location at moment 1, which is 1.5 meters. The fourth question, which we ask just for completeness, is spring potential energy, and since there are no springs, there's no spring potential energy. At moment 2, we ask ourselves the same 3 questions. Do we have translational kinetic energy? Yes, we do. 1/2 the mass times the velocity at moment 2 squared. At moment 2, do we have rotational kinetic energy? Yes, we do. 1/2 moment of inertia times the omega at moment 2 squared. However, at moment 2, we have no gravitational potential energy because we're at y equals 0, and there are still no springs in the problem. Dropping the zeros, we see the more compact form of this equation as follows. The potential energy at moment 1 is divided between two forms of kinetic energy at moment 2, translational and rotational. Examining this equation in detail, there are two variables that you would rather eliminate. These two variables are moment of inertia and angular velocity. So let's proceed. Since our object is a hollow cylinder, the moment of inertia is its mass times its radius squared. Since the object is rolling, we will have a relationship between the angular velocity and the linear velocity such that omega 2 is equal to velocity 2 over the radius of the cylinder. When we plug in these results, we find the following. This expression yields a very convenient cancellation because the r squared from the omega term will cancel the r squared from the moment of inertia term. We would then have half mv2 squared plus another half mv2 squared, leading to 1 mv2 squared. After canceling the masses, we find the result that g times 1.5 is v2 squared, so that v2 is 3.84 meter per second. Let's perform an identical analysis on the solid cylinder. Again, we choose energy methods, the first step of which is to identify the moments, and we will connect moment 1 to moment 2 using energy principles. The first question we ask ourselves is whether there is any work due to non-conservative forces, and there is no work due to non-conservative forces, meaning that this quantity is 0. Therefore, we approach this calculation via the technique of conservation of energy, which is formulated by setting the total energy at moment 1 equal to the total energy at moment 2. Since we currently understand two forms of kinetic energy, translational and rotational, we have 4 questions to ask ourselves at each moment. At moment 1, there is no translational kinetic energy, there is no rotational, there is gravity of an amount mg times the height at moment 1, which is 1.5 meters, and there's no spring. At moment 2, we have an amount of translational kinetic energy, which will be 1/2 the mass times the velocity at this moment squared. We also have rotational kinetic energy, since the object will be rolling, of 1/2 the moment of inertia times the omega at this moment squared. But we have run out of gravitational potential energy, and there's no spring, yielding the compact form mg 1.5 equals 1/2 mv2 squared plus 1/2 I omega 2 squared, indicating, just as for the hollow cylinder, that the original amount of energy, mg times 1.5, is then split between the translational and rotational kinetic terms. The split ratio depends upon the moment of inertia. So we will eliminate from this equation the moment of inertia and the angular velocity omega 2. This time, since we have a hollow cylinder, the moment of inertia will be 1/2 the mass times its radius squared. However, just like last time, the omega 2 will be related to the velocity at moment 2 divided by the radius r. Before we proceed to the next step in this problem, I'm going to take a small diversion. Currently, your screen is blank. What I'm going to draw onto the screen, so that it appears very suddenly before you, is a road sign. And what I would like to ask you is to read this road sign out loud the moment it appears before your eyes. Get ready. Here it comes. Read the road sign. It does not say cows in the clover. Read it again. This road sign says cows in the clover. It's a very human thing to look at this road sign, to see that the word is repeated twice, and delete this in your mind because you know it's a mistake. Now the question is, why did I introduce this strange diversion at this point in a rotational kinetic energy problem? Let's go back and look at our equation and maybe we can get a clue. We have an equation containing the term 1/2 moment of inertia times omega 2 squared. We are then to plug in a moment of inertia of 1/2 mr squared. Just in the same way your mind deletes the double "the" from the signs cows in the clover, students year after year will plug in 1/2 mr squared into 1/2 I omega squared, and yet their result will only contain a single 1/2. We need to be more careful than that if we want our answer to be correct. So let's proceed. Our equation will yield mg times 1.5, 1/2 m times v2 squared, plus cows in the clover. Just as previous, there are a number of remarkable cancellations. The radii will cancel entirely, as will the mass. However, on the right-hand side, rather than half mv squared plus another half mv squared, we have half mv squared plus a quarter mv squared for 3/4 mv squared, yielding us the result that g times 1.5 is 3/4 of v2 squared, leading us to the numerical result for v2, 4.43 meter per second. And when we compare this velocity of the solid cylinder to the prior result we got for the hollow cylinder, we find we have a winner, and the winner is the solid cylinder, because having a lower moment of inertia, it places less of its energy into the rotation, leaving more for the translation. Higher velocity wins the race.